Okay, chemical formulas as conversion factors. So we've been studying chemical formulas. We've been learning how to name and write formulas for compounds. Those formulas can be used as conversion factors between amounts of compound and amounts of element and lots of different things. So before we get into that, we're going to start with something a little simpler and more familiar, such as how many leaves would be on 14 clovers. So here's a picture of a clover. We're not talking about 4-leaf clovers. We're talking about the regular old 3-leaf clovers. So there are 3 leaves on every 1 clover. So how many leaves would there be on 14 clovers? Well, 14 times 3, right? So this is a conversion factor, 3 leaves to 1 clover. We want to know how many leaves, and we're given the number of clovers. So we're starting with clovers, and we're going to number of leaves. And it may seem a little silly to write that out. Maybe it is. 14 clovers. And then we're going to multiply by a conversion factor, and we want leaves on top, and we want clovers on the bottom. And then we need the relationship between leaves and clovers. And we don't have to think too hard about that. We know that there are 3 leaves on 1 clover. It would be silly to say that there's 3 clovers on 1 leaf, right? That doesn't make any sense. 3 leaves per 1 clover. Yeah, I'm not going to do math in my head today. It never works out well. 42. So 42 is the answer to this problem as well as to the question of life, the universe, and everything. 42 leaves. Any questions? You need to be able to set it up like this. I know that some of you can just do this in your head. That's great. But when we get to moles of hydrogen and moles of water, you're not going to be able to do it in your head. Or you might be able to do it sometimes. We want a sure thing, and we want to be able to write it down so we can look at it later and see how we got the answer. We can do problems like this with other things. We could ask, well, if you had 2 spiders, how many legs would there be? Well, we know there are 8 legs per spider, right? So 2 spiders times 8 legs per spider. And we know that we multiply because we want the units to work out. So spiders cancel and we end up with 16 legs. We could do that with legs on a chair. My mom was always asking me, how many legs does a chair have? Did your mom ever do that to you when you were tilting back your chair and sitting on only 2 legs? My mom would say, how many legs does a chair have? And that meant you were supposed to sit with all 4 legs on the ground. Silly question. Look at this water molecule. In this one water molecule, bless you, there are 2 hydrogen atoms and 1 oxygen atom. There is a conversion factor in the chemical formula. Here's the chemical formula, H2O. In every one of these molecules, there's 2 hydrogen atoms. There are several conversion factors hiding in each chemical formula. So just like there are 4 legs in 1 chair, there are 2 hydrogen atoms in 1 molecule of water. So the relationships in the chemical formula allow us to convert between moles of the compound and moles of an element within the compound, or the other way around, vice versa. So if we look at this molecule here, this is carbon tetrachloride, we see that there are 4 chlorine atoms in this 1 unit, right? 4 chlorine atoms. Well, this isn't atoms and molecules now, this is moles. But mole is like a dozen. Let's go back to the chair. So here's the chair. What if I had 12 chairs? How many dozen legs would I have? 4 dozen, right? The relationship between numbers, 4 legs and 1 chair, works with dozens also, because a dozen is just 12 things. So there would be 4 dozen legs on 1 dozen chairs. When we talk about moles, that's just a number that's a wee bit bigger than 12, right? It's Avogadro's number of those molecules, and there will be 4 times Avogadro's number of the chlorine atoms. Any questions? So let's find the number of moles of oxygen in 18 moles of carbon dioxide. So we have 18 moles of CO2. And what do we want to find? Moles of oxygen. So I want to multiply by moles of oxygen, and mole of CO2 is a unit. I want that unit to go away. So those cancel out. And then where do I get the relationship between moles of oxygen and moles of CO2? From the formula. I look at the formula and I say you could do it in molecules if you want. 1 molecule, I hate writing this word, 1 molecule of CO2 contains 2 atoms of oxygen. And we can also say that 1 mole, remember, is the chemist doesn't, it's not an abbreviation for molecule, even if I think it should be. 1 mole of CO2 is equal to 2 moles of oxygen. So then here, I've got 2 moles of oxygen for every 1 mole of CO2. It's like wheels in a bicycle. On one bicycle, there are 2 wheels, right? So now I just do the math here, and I end up with 36 moles of oxygen. Any questions? I have a question. So this number 2, is that an exact number, or is there uncertainty in that number? It's exact. Just like the number of legs on a chair. It's really a counting number. It is exact. There are exactly 4 legs on a chair. And so in this molecule CO2, there are exactly 2 atoms of oxygen in the 1 molecule. There are exactly 2 moles of oxygen in 1 mole of carbon dioxide. Let's find the moles of oxygen in 1.4 moles of, what's the name of that? Oxyacid. What's the name of SO4? Sulfate. So sulfate, we change 8 to ic, so this is sulfuric acid. So we're supposed to find the number of moles of oxygen in 1.4 moles of sulfuric acid, H2SO4. Well, what's the relationship there? 1 mole of H2SO4 has how many moles of oxygen? 4. How do you know that? The formula. It says it right there, 4. SO4. So 4 moles of oxygen. Now, if we were looking at sulfur or hydrogen, it would be a different number. It wouldn't be 4. So 1.4 moles of sulfuric acid So I want to find the number of moles of oxygen. So I'm multiplying by moles of oxygen. I'm dividing by moles of H2SO4. One mole of H2SO4 has 4 moles of oxygen in it. So I take 1.4 and I multiply by 4. and I get 5.6. And the unit is moles of oxygen. If we're considering significant figures, which we should always do, our first number here, 1.4 moles of sulfuric acid, was that exact? No. That's an estimate. There's uncertainty in it. So this has two significant figures. This ratio is exact, and so my answer should have two significant figures. Any questions? Well, converting between moles of one thing and moles of another thing is nice, but we don't measure things in moles. We measure things in grams. So this kind of goes back to the question we talked about at the very beginning of the chapter. The USDA recommends that you consume no more than 2.4 grams of sodium. How much sodium chloride would that be? So we want to know what mass of sodium chloride contains 2.4 grams of sodium. Well, this formula gives us a relationship between moles of sodium chloride and moles of sodium, but it doesn't give us the mass. I think I was supposed to do something else there. Okay, let's do something else here. Sometimes I forget what I have in my slides. Well, from the formula, we can say that 1 mole of sodium chloride is equal to 1 mole of sodium. All right, that's what we just learned how to do. The question that we're being asked here is what mass of sodium chloride? So we're trying to find grams of sodium chloride. And we're given a mass of sodium, 2.4 grams of sodium. We have this relationship that ties sodium chloride to sodium, but it's in moles. Could we get from grams of sodium to moles of sodium?
Yes.
Yeah, we could. We learned that earlier. That's the molar mass of sodium. So we could get to moles of sodium. This relationship that we got out of the formula would allow us to go from moles of sodium to moles of sodium chloride. And then using the molar mass of sodium chloride, we could get to grams of sodium chloride. So there we have a path with 3 arrows. 2.4 grams of sodium. That means we're going to have 3 conversion factors. This is where dimensional analysis becomes really, really useful in chemistry. So I want moles of sodium. I want moles of sodium chloride. And I want grams of sodium chloride. I made my path, and then the units in the path are the units in the numerator. Grams of sodium, moles of sodium chloride, grams of sodium chloride. I take the first unit and I make it the denominator on that second fraction, because I want that unit to cancel out and go away. There's too many units floating around. Put moles of sodium down here so that the units cancel out. And moles of sodium chloride down here so the units cancel out. Personally, I think this middle one is the easiest one. What's the relationship between moles of sodium chloride and moles of sodium? It's 1 to 1. In every 1 mole of sodium chloride, there's 1 mole of sodium. We need that in there, though, so the units work out. Okay, so how much does a mole of sodium weigh? We have to look at the wall. 22.99. On the periodic table is the molar mass of sodium chloride. I'm sorry, sodium, 22.99. And then we have to do a little bit of math to get sodium chloride. For sodium chloride, we have 1 sodium, which is 22.99, and we have 1 chlorine, which is 35.45. And we end up with 58.44. 58.44 grams of sodium chloride is equal to 1 mole of sodium chloride. 1 mole of sodium chloride, 58.44 grams. Now we just do the math. You go from left to right, multiply by the top, divide by the bottom. 2.4 divided by 22.99 times 1 divided by 1, that's not going to change anything, times 58.44 equals, and because I started with 2 significant figures and everything else in there is either exact or has more, I'm going to end up with 2 significant figures, and I'm going to get 6.1 grams of sodium chloride. So you could eat 6.1 grams of salt and not go over your sodium intake as long as nothing else you ate that day had sodium in it. But most of the things we eat do have sodium in them. Any questions? That's a lot of salt. Okay, determine the mass of oxygen in a 5.8 gram sample of sodium hydrogen carbonate. We should be able to write the formula for that now. Here it is, sodium, and this is the hydrogen carbonate ion. So if we have mass of a compound and we want mass of an element, we're going to have to use moles in between. So we are given 5.8 grams of sodium hydrogen carbonate, and we want mass, just trying to stay on the same line here, we want grams of oxygen. So what can we figure out here? We can get mole ratios. Oh, where am I going to put that? I'll just stick it right here. 1 mole of sodium hydrogen carbonate has how many moles of oxygen? 3. 3 moles of oxygen. It's right there in the formula. It says O3. And then other things we might need would be molar masses, but we can figure those out later. We can go from grams of sodium hydrogen carbonate to moles of sodium hydrogen carbonate. And this relationship here allows us to convert from moles of the compound to moles of the element, and then we can go to grams of the element. Everybody okay with the path? Once you get the path set up, it's just following a pattern after that. 5.8 grams of sodium hydrogen carbonate. There are 3 arrows. I need 3 conversion factors. So grams to moles, so moles of NaHCO3. It is important now to write moles of what? Because if you just write moles and moles and moles and moles, you might get some of the numbers in the wrong places. Grams of oxygen. So I would get moles of oxygen down here, so the moles of oxygen cancel out, and the moles of sodium hydrogen carbonate cancel out. And I got grams of sodium hydrogen carbonate down here. And so those cancel out. I like doing the mole ratio first. So we wrote it down. 1 mole of sodium hydrogen carbonate equals 3 moles of oxygen. Moles of oxygen is on the top, and so the 3 goes with the moles of oxygen, and the 1 goes with moles of sodium hydrogen carbonate. And then over here, I've got grams per mole of oxygen. That's the molar mass. I just look at the periodic table. 1 mole of oxygen weighs 16.00 grams. Then for this guy, I need to do a little calculation. Sodium hydrogen carbonate. So 1 sodium, 22.99, and 1 hydrogen, and 1 carbon, and 3 oxygens. I would really encourage you to write down, what I'm writing here is what I think is the minimum that you should write down. You should write this down because if you get the answer wrong, you can go back and look. Well, did I do this part correct? Did I do that? Where was my mistake? 22.99 plus 1.008 plus 12.011 plus 3 times 16. 84.009 grams is equal to 1 mole of sodium hydrogen carbonate. Now that would really only have like 4 significant figures. Um, 84.009. If I look at my significant figures before I start doing the math, here I've got 2 sig figs. This one has 4. This is exact. That has 4. My answer is just going to have the 2. So I do 5.8. Well, that would be a 1 up here. You can multiply by 1 if you want to. Divide by 84.009 times 3. Divide by 1 if you like. Times 16, divide by 1, and I'm going to get 3.3 grams of oxygen. My calculator is showing me 3.31393065, but I just need the first 2. Any questions? These are harder to do in your head. I don't like to do these in my head. I write these down because I like getting the answer right. So I would encourage you to write them down too.